So again, we're always going to be thinking of our circle. We're always going to use the strategy of draw a triangle. The cast rule is going to come into play a fair bit as well. So for this one, if cos of theta is 3/8, could we draw that triangle? What quadrant or quadrants would it be in? Okay, it's going to have to be in quadrant 4. Now, if it just told us cos equaled 3/8, you know right away it could be in 1 or 4. But then since it's not in quadrant 1, we know we have to draw an angle in quadrant 4. And when we make our triangle, because there's two options here, you can make it to the y-axis or to the x-axis, we always make it with the x-axis so that our reference angle becomes part of it. Cos is adjacent over hypotenuse. A squared plus b squared equals c squared. Try to do it in your head again. This one we have our hypotenuse. How did you do? Root 55. 64, which is 8 squared, minus 9, which is 3 squared, is 55, so it'll be the square root of 55. Notice that I label it all with positive values because I'm thinking about the actual triangle. But now when we go to write down what sine of theta would be, well, sine is opposite over hypotenuse. We use our reference angle. So we know that root 55 is the opposite, 8 is the hypotenuse. And because it's in quadrant 4, sine is going to be negative. Tan, opposite over adjacent. And because it's in quadrant 4, you know tan is negative. What this unit opens up is once we get introduced to radians and once we get introduced to the unit circle, there's just a whole bunch of questions that use those three big ideas that we can now answer. For example, is this point on the unit circle? First of all, it's not one of the ones that we did today with 30, 45, and 60, right? But despite the fact that we learned 30, 45, and 60, can you see that those are only 3 points in the first quadrant? That there's an infinite amount of points in that first quadrant that we don't even know the coordinates of. Could it possibly be that root 3 over 3, root 6 over 3 is one of them? Could be, but it could also be that this point just is off by a little bit and isn't part of it. So how would we know? We could use a formula. Which formula are you thinking of? So we've got our formula for our circle, which is also one of our big ideas, right? Cos squared plus sine squared equals 1. And remember, our x-coordinate is the same as cos, and our y-coordinate is the same as sine. So if this is the formula, what we want to check if root 3 over 3, because that's our x-coordinate, plus root 6 over 3, is that equal to 1? Okay. Notice the way that I wrote this so far. I wrote out a statement. I don't know if it's equal to 1 yet. That's what I want to show. I either show that it is equal to 1 or it isn't equal to 1. So when I wrote this statement, I said I want to check, kind of looks like cheek, but let's make that a better C. There, check if this is equal to 1. What I'm going to do is I'm going to just put a line here because I don't know that they're equal. And there's marks taken off if you make things equal before you prove that they're equal on the final exam. So one way to avoid that is just separate it with a line. My right side of my equation is equal to 1. I want to see what my left side is equal to once I simplify it. And root 3 over 3 squared is root 3 over 3 times root 3 over 3. When I multiply the bottoms, I get 9. And root 3 times root 3 will just be 3. Yes. Yeah, at the top, you could say, I want to check this. And then at the end, if they come out to different numbers, like if one side's 1.2 and the other side's 1, then you would say, since they're not equal, we know it's not on the unit circle.
Yeah, can you put like you just have a non-equal sign?
Like this?
Yeah.
If at the end they're not equal, you could write that at the end. Yeah. Same thing, though, we want to put the line before that, because we don't know if they are or aren't until the very end. And when we square root 6 over 3, we're going to get 6 over 9, which adds up to 9 over 9, which equals 1. So exciting. So is the point on the unit circle? Yes. And of course, if it didn't work, then you would know it's not on the unit circle. Now here they're telling us that it is on the unit circle. We need to find our other coordinate y. Now we could use a similar strategy that we did to the last one, and it would work. You can use x squared plus y squared equals 1 and just used fractions. That'll work. What I'm going to recommend, though, is if you use triangles, you're going to have less fraction work and you're going to make less mistakes. So again, we're going to use the big idea. Our x-coordinate is cos theta, and our y-coordinate is sine theta. And if we actually draw a triangle, tells us it's in quadrant 3, and we make a triangle in quadrant 3, and cos is adjacent over hypotenuse, so I'm going to say this length would be 12, this length would be 13. We could do a squared plus b squared equals c squared. This one you might need your calculator for, or maybe you recognize this as a fancy triangle where all the sides are nice, like 3, 4, 5. And you get 5, 12, and 13. This would be your reference angle. What's y? Well, y is sine theta, and sine theta would be opposite over hypotenuse. And since it's in quadrant 3, it would be negative as well. Now it asked us to find y. So as your final statement, you need to say what y equals. Even though it's implied when you say sine theta, you still need to show that you know that y then is equal to negative 5 over 13. Now this is a big triangle. If I drew our little unit circle, if that's 12, unit circle would be just a little cutie. Right? It'd just be tiny because it has a radius of 1. And this point right here, proportionally, would be negative 12 over 13, negative 5 over 13. That's what we actually found. But when we draw the triangle, we may as well draw the big triangle so we don't have to deal with fractions. And we're able to solve it the same way.